Welcome to the talk sponsored by SNIA, where we're going to talk about all things persistent memory, what the trends are, and we have some great panelists for you today. I'm Dave Eggleston. I'm representing Microchip, but just as the moderator and ringleader of this panel, we'll get into the topic shortly. A few things that I'm going to present here. And let's get to our slide at the top. This is a live webcast, as I mentioned, sponsored by SNIA. Very specifically, it's from a work group called CMSI. I'll talk at the end about if your company is not a member of SNIA, how you can join, and then also the CMSI, how you can join. So we'll cover that all the way at the end. This is the legal notice. And this is just, I'm required to show this. I love the part at the bottom that says no warranties. No, we don't warrant any of the work or the opinions expressed during this webinar. So use at your own risk. Love that disclaimer. So who are our panelists? Our panelists today are going to be Pekan Gupta. He's a business strategy specialist at Intel in their FPGA group. We have Gary Kotzer. Gary is the storage CTO at Marvell. David McIntyre, who's Director of Product Planning, Business Enablement at Samsung. And then Andy Mills, who's Senior Director, Advanced Product Development at SMART Modular. So let's get our lovely presenters' faces up here and kick this off in entertaining fashion. Let's wrestle with the big elephant in the room. For a while now, we've associated persistent memory with Optane and Optane with persistent memory. But Intel has recently announced last year that they're not going to continue to support that product long term, and they stopped development of that memory technology that goes into Optane. So is persistent memory dead? Or have we need to think about it in a broader way? How do we redefine it? So let's have that as our first topic here, gentlemen. How do we redefine persistent memory? And I'm going to go to Andy Mills first. Andy Mills from SMART. Good to have you on board, Andy. Go ahead and chime in. How are you thinking about persistent memory personally? And how is your company thinking about persistent memory and the opportunities? Is this dead, or is there some life here and we should grab hold of that?
Well, I get to define the obvious here that persistent memory is memory that is persistent when the power goes away, right? Essentially, you're storing stuff at memory speeds. So in our definition of the world at SMART, an NVDIMM is our primary product here, is something that operates like a memory, but when the power is lost, that data is saved, is persistent. And so when you come back, it's restored. And from that standpoint, there are plenty of applications that still need that. I mean, that's a very, very important feature and requirement going forward. I think Optane did a lot to help enable that infrastructure, and put in place a lot of the things needed, both at BIOS level. There's many things that have to collaborate in a system to make persistent memory work, right? And
so let's jump to David McIntyre, because David, your company, Samsung, your company makes some memory technologies and probably explored even making a technology similar to what Intel was doing. But your primary products are in memory are DRAM and NAND. I mean, does that make sense to combine DRAM and NAND to do persistent memory?
Sure. So Samsung has a concerted effort to build out, I call it the value-added portfolio of SSDs and memory products from both directions that can complement each other. I'm very focused on application support and development in that regard, where we talked about at the beginning persistence and what that means. It really depends on the application requirements from a persistence standpoint. The good works that SMART has done on NVDIMMs continue forward. I would suggest that the Intel solution was more of a mid-tier caching solution. There's more work to be done at the application shim to engage the requirements of those applications from a persistence standpoint.
Well, we'll come back later and drill down more. You know, you mentioned quickly on the NVDIMM, SMART was putting that energy source inside the container, which had the memory. But let's keep focus on that NAND plus DRAM and kind of redefining. I do remember that one of the godfathers in the SNIA activity here was Andy Rudolph at Intel. And he used to talk about, hey, I don't care if it's DRAM with a giant car battery. You know, that makes it persistent. That's good enough. So let's think about the architectural impact and how to approach it in the architecture of a rack, of a server rack. So Gary, from Marvell, how is Marvell thinking about this, and how are you thinking about persistent memory? How should we define it?
Well, I mean, if you're talking about defining persistent memory, I kind of start with what Andy was alluding to, that it is persistent. But the odd thing is that whenever you look at how people were finding the most value, it was really more the fact of, I have this memory that it just happens to be persistent, but it's really large capacity and it's much cheaper than DRAM. And even though it did have lower performance, they still saw a lot of value in the fact of, I don't have to end up having to have OS, I just lost the term here, but anyway, that I have paging going on. And paging in itself, took up a lot of time. So being able to have the slower memory, but still close to DRAM, but larger capacity, I was much more efficient in how I utilized that. And so I think when people think about persistent memory today, it comes along the lines of what was defined by Optane, in that I have this media that is targeted for memory-based accesses, and it can, in this case, load store.
Right. And I think that's a difference we're going to pull out here in a bit, that storage is done in blocks, files, different constructs there. And then we think more about memory, really kind of serving the XPUs, whatever they are, and getting that cache line in and getting that operation going inside. Pecan, how is Intel and your group, and particularly FPGA group, thinking about persistent memory and how we should define it? What's your thoughts there?
Sure, Dave. So at Intel, we think persistent memory more as a concept and a technology rather than an implementation. And that technology has two pieces. One is the data should be preserved across power cycle. Now that power cycle can be planned or an unplanned abrupt power fault, right? So that's persistent part of it. And then the data should be accessible at cache line or byte line granularity using standard memory semantics, load and stores. So that's the memory piece. So combining these two attributes, preserving the data across power cycles and accessing it as a load and store, makes it persistent memory. Now, that can be implemented with any combination of DRAM and NAND. It can be implemented as a 3D cross-point media or any phase change media behind it. And especially with the FPGA division, we are thinking even a step beyond that. If your memory pool can be disaggregated from the system, put into a different rack, and that rack is power fault tolerant, it itself is a persistent memory, because you are accessing that memory over the cables through a standard memory load and store interface, and it's fault tolerant because it's preserved across power cycle.
So we'll definitely come back around to that whole topic of disaggregation, because I think that's going to be a core theme here, and dive in on why we want to do that. But let's drill down a little bit more on persistence itself. Is persistence good or evil? Which is it? Do we like it? Do we not like it? Does it create problems? I think, Gary, why don't you kick us off there? Because, you have a long background in storage. Storage is obviously persistent. So there's something good about persistence. But when we put persistence into memory, is that really a value proposition?
Let me just say, I think that, whenever a new technology is introduced into the industry, timing is everything. And whatever you look at, let's go back to the Optane case. I think most people saw that there was a lot of value around Optane. And as I mentioned before, they really saw most of the value around this high capacity, much cheaper much cheaper medium. But I think that us being human, that we don't want to make too big of changes into the infrastructure. We tend to take small steps. And so the small step was to go ahead and use this persistent memory as a much larger memory, like DRAM. The persistence, I think, will come later after we get, the big bang value out of using
I see.
cheaper
So
memory.
we're starting
And
first
then once it becomes prevalent, then they'll start tackling the value of persistence.
So I think what you're saying is we're seeing in the memory space, we're seeing more innovation right now about how we're putting memory together. And that in a lot of cases, that's still DRAM. That's volatile memory. That could be at HBM level, that could be at DDR level. And now we have this new thing, which is CXL is entering the picture and allowing us to attach DRAM through a CXL interface. So David, back to you at Samsung. I mean, I think how now we're kind of getting this idea that persistent memory can be around as this combination of NAND and DRAM. But what are you seeing with just DRAM alone and attaching on this new CXL bus? And how will that, one of the things is, will CXL attach DRAM? What does it do for us at system level? And then does it threaten the DDR dominance in server memory?
Yeah, so CXL and the ecosystem is embracing it. It's a means of making better utilization and optimizing the resources available from a memory standpoint in memory pooling, memory semantics. The numbers say that maybe 50% of memory infrastructure is actually deployed at any given time. So CXL provides that means of coherency and the ability to make better use of those resources. And so Samsung has a concerted effort on multiple fronts to support CXL platforms, whether it's SSDs or memory expanders. So that, compared to persistent memory, I just came up with a COA term, continuity of application. There you go. So
okay.
Yeah. So
that's not CMOS over array or one of these other acronyms that we jargon around and nobody knows what the hell it means. Andy, you've also been in the storage business for quite a while, but you've also been looking at DRAM. I mean, what do you see about it? CXL has just come on the scene here. I like to say it's at the peak of the Gartner hype cycle. It cures cancer. It does everything for us right now. But what does CXL attached DRAM do it from a system perspective?
It solves everything.
Wow, that's great. When do I get it? And when
exactly.
does this improve my life?
I think Dave said it already. I think, and Gary to a certain extent as well. I mean, the capacity is king, right? I mean, what we're seeing is this migration of applications out of traditional tiered storage like applications where SSDs were good enough for many applications. And then suddenly IoT ingest a lot of data and people want to put stuff in memory, right? And process it in memory.
Why? Yeah, tell me more about that. Why do you want to put it in memory? What's better about load and store versus an IO access?
Well, speed, speed, real time. Everyone loved the iPad versus their old wait 10 minutes for your PC to boot up scenario. It's the same kind of thing, I think, in application world. So you're looking at, people wanting to get responses within seconds or less than seconds now, whereas it would take maybe 10 minutes to process something, and there's been some.
So let's put a finer point on that. So from a processing unit going out to DDR and coming back is, could be between 50 and 100 nanoseconds, right, of latency. And how much data are you getting in that time?
Well, I think it's the disconnect between CPU and memory, right? You got the CPU cores and power and all that kind of stuff coming up. One of the things
but I guess what I'm trying to get at is we're going to have a certain latency. Let me jump to Pecan. You're going to have a certain latency. And my understanding is from the processing unit is trying to grab a cache line from memory and just grabbing a cache line at a time. And of course, this is filtered through multiple layers, L1, L2, probably L3. Now you're coming out to DDR. But Pecan, tell me a little bit about what's that latency look like right now? And then with CXL, boy, my understanding is we're going outside the box now. So we have a longer latency. What does that look like in terms of latency?
So Dave, to answer that question, adoption of any technology depends on continuity of application, which is what Dave said. And in this case, latency is one of the prime factors which will be the deciding factor for adoption of any persistent memory implementation. And we are looking at 1 NUMA hop to 2 NUMA hop latencies. Anything beyond that will make it unusable for most applications. So even if you have a persistent memory solution which is very cheap but has a very long latency, it's difficult to adopt.
Okay, so I get it. Right now, if a processing unit, and we see them increasingly using it in the data center using HBM, there's a certain latency to go to HBM. I know how long it's going to take and then come back. With DDR, there's a JEDEC spec, which tells me as I go from DDR5 right now, as I go out to DDR5 and come back, that's a certain amount of time. But when I go out to CXL, boy, that could be non-deterministic. Gary, how is this handled? Because I've seen an interesting demo from Marvell where you're showing how you're now sharing and doing memory accesses between boxes and between servers,
Right.
and basically mapping that memory that's in another server into your local server space. But that latency is going to be different. So maybe talk a little bit, first of all, about Marvell's, what you're doing there with sharing memory across the network. And then how do you handle that latency difference?
Well, I think it goes back to what Pecan was saying, is that, today, systems are used to having that 1 NUMA hop. And,
and define a NUMA hop. Yeah, define a NUMA hop, because SNIA, we often have people come from storage and they don't know some of our memory terms. So please define that.
Okay, so whenever you're accessing memory that's connected directly to the processor across DDR, that's called a near memory. Whenever I go across the processor interface bus, or called UPI in the case of Intel, I go to his memory, that's called far memory, and that's considered to be 1 NUMA hop away. So,
and how long is that? How long does that take, a NUMA hop?
I would say it's probably
allowed?
about 100 nanoseconds on average.
Okay.
That's the right assumption.
Okay.
Got it. Okay,
So,
keep going, Gary.
So, I think whenever you look at that latency, there's going to be a range where it becomes intolerable for the processor to handle it, because you start stalling his pipeline. And so you want to be very careful about maintaining that latency. So as you said earlier, David, you have memory that's going to be local, and that could be CXL. And as long as we stay within that NUMA hop, we're okay. And whenever we want to go external, and we have some cases right now with memory pooling and the appliances, it is desirable to try to maintain that within that 1 NUMA hop, if at all possible. And I think that is the goal at this point in time.
But what if we don't? My understanding of, again, CXL attached memory is that it allows much greater bandwidth. You can basically get this massive fan out to lots of memory. And then, but now we're talking about going from a deterministic length of latency that I know what I'm getting with HBM, I know what I'm getting with DDR, but now I've got this gray area. And it's not just near and far. I don't have these specific defined terms anymore. Now, one advantage with CXL is that device can tell me what its latency is, so I can plan on it from the processor. I seemingly can schedule it, or I could take transactions. But Andy, how do you see this continuum of latency that we're going to have on the CXL attached memory when we go out to it beyond DRAM, beyond DDR DRAM?
Well, I think that's been one of the debates that's been going on in both internally and in the industry a lot, on how exactly will this CXL memory present itself to the operating system and the applications. Does the application need to be aware that it has two classes of memory, one at low latency, one at high latency?
But is it just going to be high latency? Again, low latency, if it's DRAM, it's defined by a JEDEC spec. But high latency, again, is kind of this gray, I see this gray area. Are we going to have bands? Are we going to have tiers with definitions with them? Is that going to be standardized?
Good question on the standardization. I think the standards will take care of what CXL memory latency, limits are potentially, but there's a lot of application work to be done. As we start to engage with customers on CXL, we're starting to get the sense that this is the year of learning. Next year will be more of a year of deployment, but this is the year where people want CXL product in hand. They want to play with it. They want to see exactly how their applications are going to be able to use or respond to it. And the word tiering always comes up in those discussions. And in terms of, do we need special software? There are certain companies out there offering some software to do tiering.
Yeah, maybe talk about who some of those companies are that are bringing those software solutions in.
Well, I think the most visible one, Memverge, has been out there for a while, right? Pushing that. Those guys have been very, very active in that area.
Now, I've also seen VMware a little bit with their Capitola project, trying to handle different, different types of memory.
I think it becomes the domain of the operating system guys. A guy who's been very involved in tiering and caching, over the years. On the storage side, we saw that eventually disappear or get merged into the operating system. So I think the operating systems have to get better at knowing how to use these different classes of memory. They've done it in storage. I think you saw Windows with storage spaces, you saw Bcache, Btier, and all that kind of stuff appear in Linux. But it took a couple of years once the devices had been out there for a while. So
okay, now I'm starting to get the picture. So again, we're going to have all these different devices. We're going to have different tiers, whether it's HBM, DDR. Now I go up to CXL. That could be, again, kind of this gray area or different tiers. Could be networked, etc. Okay, so now we have a system, an architecture that can handle these different latencies, and that may be software driven, etc. David, your company, Samsung, ships an awful lot of SSDs, and including NVMe SSDs. And one nice thing about CXL attached memory, whether it's DRAM or persistent memory, is that it uses PCIe electricals, just like NVMe SSDs use the PCIe electricals. Are we going to see CXL attached SSDs?
The tea leaves look that will happen.
Yeah, why? Why? Because, we were just talking about NUMA hops and keeping in 100 nanoseconds. I don't think the latency to an SSD round trip is going to be 100 nanoseconds. How's that going to come together? And why? What applications would drive that?
So a couple of things. One is by having CXL SSDs, and I mentioned earlier that we're building out a portfolio of smart SSDs. There's a memory-semantic SSD that we showed.
Yeah, talk about that more. The memory-semantic SSD is a particularly interesting NAND and DRAM combination inside something that has one interface, which is that PCIe electricals. Please talk about that.
Right. So CXL, as you said, it runs over PCIe electricals, and the memory semantic SSD is just that. It focuses on memory semantics and more tuning the tiered memory and storage support around this particular application. So you asked about what sort of applications. The Smart SSD portfolio, I have it targeted at data analytics, data function management offload, and also security. Security is another elephant in the room, right? So being able to detect intrusions and maybe nefarious acts through assessing read-write behaviors, that's where it's very important to have that caching mechanism available for real-time analytics and determinism that there is an issue to deal with. And determinism can be defined. I harp a lot on applications and focusing on what the end users and customers expect. Probably a good thing to do. So, determinism, I was actually talking with a gentleman from Meta a year or so ago, and he was telling me that, look, it really doesn't matter what I think. It matters what my daughter, who's on Facebook, thinks, because if you interrupt her service, I'm going to hear about it. And so from his standpoint, determinism, as long as it's, if we're doing garbage collection on the drive level, as long as that's done in the background and we're not impacting the application performance, that's a good thing, because he's not going to hear about it from his daughter.
So we're gonna jump in with one of the viewer questions here, which is relevant to this, and it said CPUs will have to have a longer tail latency tolerance, and application awareness is not enough. Is that happening in the CPU space? Is Intel, is Ampere, is AMD, is AWS the Graviton processor? Are they getting ready for these long tail latencies? Pecan, why don't you tackle that one?
Yes.
What are CPUs doing about this? Because it can't just be software alone. It can't just be the application. The CPU has to allow that.
Yes. So Dave, that's a very good question. And actually CPUs are working on that. So before I jump into the CPU side of this discussion, I want to open up it from a broader use case perspective of persistent memory. Persistent memory is used in two ways. One, to do checkpointings, which is what the write ahead log for OLTP kind of transactions is. And the other one is to recover or reboot quickly. That's where the second part use case comes in. Now, when you do checkpointing, you are just writing a snapshot of the data into the memory. You may not be reading it back immediately. So in that case, a longer latency may be absorbed, maybe okay for an end application. And those are the cases when if you have a device or an implementation of a persistent memory which has a higher latency than the others, it may still fit the use case. But then the other side of use cases are when you want to reboot quickly from an application or migrate your VM from one container to another one very quickly within milliseconds or much less than that. That's where you have to live with a persistent memory device which has very low latency. So it's again going back to the same point. Different applications have different requirements or have different tolerances of latency. And that determines which architecture you choose or which implementation you choose for a persistent memory device.
Got it. And let's take another one of the viewer attendees' questions, and we'll see who on the panel wants to tackle this one. It's a good question that's relevant to this, where we're dealing with how are we going to handle these latencies? As you point out, the CPUs themselves are doing work. The CPU vendors are doing work to allow that. The CXL protocol itself does allow that. And this is relevant. And it says, how well did NUMA prepare the industry for the wider range of memory latencies that CXL and UCIe will present? We haven't talked about UCIe on the low end, but NUMA already had to deal with near DRAM single hop and two hop. So who wants to tackle that question? Anyone want to take that on? Andy, you're never short of words. How well did NUMA prepare the industry?
I think this one's got me stumped. Gosh,
How about Gary? Do you want to weigh in?
Yeah, Gary, take a shot, Gary. You've been in computers a little bit longer than many of us here. So
nice detour there, Andy.
Thank you.
I
think he just called you old.
Well, I think this kind of goes back to what, some of the threads that have been going through this is that, the industry doesn't move very quickly. And yes, the processors have been having to deal with NUMA for a while. But whenever you start getting into these really long tails on latency, it's not something that can be tackled right away. The industry is going to try to get the biggest bang for their buck as soon as possible. And right now, they see a lot of value in implementing CXL with DRAM and some of the faster persistent memories when they're available. So I think the industry is going to be wanting to tackle that whenever these new memories come about, and they can be handled by the CXL. But again, it goes back to the fact of what Pecan was saying, beyond 2 NUMA hops. Right now, it's too much of a challenge to take that under consideration. And whenever I look at some of the use cases of where we're using NAND-less DRAM, and like in the case of this memory-centric SSD, I think we all agree it's not plug and play today. But I think there are going to be some cases of where it does make sense, where you have these small subset of applications where the data flows are well defined between the storage domain and the memory domain. And if we could replicate OS paging at that level, then that would be one way of being able to handle it.
Well, that's where tiering.
Go back. Yeah, go.
Well,
I'm
I was
sorry,
going to say,
Andy, go ahead.
Dave, sorry, yeah, just a quick interrupt on that. I think that's where the tiering concept comes in. If you look at what Amazon Nitro did, for example, with their how do you get to 24 terabytes of memory? They're going out over a network, for goodness sake. Latency there is no longer just in the 100 nanosecond range. You're talking about, way. So I think back to the question, NUMA and preparation. I don't think anyone's yet fully grasped the whole concept of what the impact of the tiers are going to be when you want to deal with 24 terabytes of memory that look like there's attached to a CPU, right? You've got latency that are going way out over the network, right to near latency, mid and far. You've got all these different tiers of latency going on. So I think, again, I go back to my comment. I'm not sure we could be prepared until we've got to play with it and put it out there.
So is that happening right now?
Yes.
That's occurring right now. And when will we see products? I think even in the case, David, why don't you chime in? Because Samsung's certainly been out in front of this, combining NAND and DRAM in interesting ways, attaching on the CXL bus. Some of these things you're going to productize. I think the memory-semantic SSD is more of a proof of concept. But when do we get these products that help us move forward and have low latency, or we can put in systems where it's non-deterministic?
There are OEMs out there today that brute force the problem by having massive DRAM banks and running in-memory databases. So that's one way to address that latency issue, is to have the DRAM locally available in a massive capacity. And then for point applications and proof of concept, Samsung has already showed a number of cases. How to choose your favorite movie was one of the demos we did at the Samsung Technology Day last quarter, where basically through memory semantics we could map the application and more particularly the read-write pattern down to a very fine granularity of 64-byte read and writes. So that deals with the contention of large block sizes and the misalignment of read and writes in that regard. So, as far as when these products come out, hang on for your dear life, because CXL is being embraced by pretty much vendors, ISVs, and end customers are understanding the value that it provides, because as we talked about earlier, the underutilization of existing DRAM resources is a big TCO cost problem.
Talk about that a little bit more. How does that scenario arise in the box of a server? It seems like there's been some good research done by Microsoft and Google that as much as 50% of the DRAM might be allocated inside the box, but not used or not used well. So it's almost like an over provisioning inside the server box.
Yeah,
how does CXL break through that?
Right, and it's one box scale to tens of thousands of boxes. That's data centers that are building out infrastructures for decades have been caught up on the Moore's Law treadmill that I just want to have my refresh cycle ready every 2+ years, 3 to 5 years maybe, in a data center environment, and the ability to support those applications, even though I don't necessarily understand what their requirements are. I want to make sure that my speed and feed treadmill is ready to do so. And in data centers, of course, you're going to have a mix of your baseline infrastructure, and then as these new DDRs come to play or CPUs come to play, there'll be that transition point to bring those new technologies in.
So what do you see? what do you see as the driving applications? Because I want to pull in one of the questions here that
Sure.
came up. And actually, I'm going to combine two of the attendee questions here. One question says, can you talk about the densities required for persistent memory applications? It doesn't seem like checkpointing or logging creates demand for high densities. And then there's another question that came in very early in our discussion. What kind of persistent memory will replace 3D XPoint at a competitive price point? And I think, of course, Samsung is making both DRAM and NAND and being a memory producer, and then also looking at the system implementation. Now, how do you answer those kind of questions? What densities do you need, and what kind of persistent memory replaces 3D XPoint at a competitive price point?
My coin term, continuity of application, there's a corollary to it, which is without sacrificing performance. And so I think the density requirements around persistent memory, however we define that to be, will drive basically how much you need. And as you're building out your solutions menu of DRAM storage and the shim layer of storage class memory, how much you need really depends on how much the application can bear from a control plane standpoint, and then also what the performance requirements are to provide the very best to those applications. So we have a vested interest at Samsung to explore from an applications standpoint, basically those working use cases, and how do we optimize that mix of technologies as we search for the killer apps where we're going to make our money from.
Got it. And we heard Gary earlier in this panel discussion talk about persistent memory, having the characteristics of persistence, but also be cheaper. Well, certainly, I think Samsung would say DRAM got a lot cheaper over the last year, and that's been a moving bar that probably has the memory industry in some pain right now. Andy, there's another question over here, since we're talking about how we combine DRAM and NAND as a cost-effective way at a system level of doing persistent memory. It says, ideally for storage, we need an NVRAM-like solution, ideally without the need for a battery or supercap pack. Yep. CXL, NVMe SSDs are all great for the next level down, but we continue to have an issue in the DRAM space. Is there work to improve the DRAM DIMM to help make it persistent? So SMART has been in the NVDIMM business, and maybe even for some of our attendees, quickly define what an NVDIMM is. But it sounds like they're talking about an NVDIMM, but boy, I don't want a supercap or battery.
Yeah, there's certain laws of physics involved here. You need energy to keep things alive, while you save them in the case of volatile memory. We at SMART, we focus on NVDIMM-N, I guess, is our focus. Optane was something that did not require a battery pack. That was the nice thing about Optane. It was a little slower, of course, but it was bigger in capacity. It didn't require that. One of the benefits of NVDIMM, of course, is it's faster. It operates more like a DRAM in terms of performance and speed, but you're trading off now some of that capacity to make room for the energy source, or you generate, you got other components on there for the NAND as well. So you've got a form, fit, and function problem. So an NVDIMM, just for those who are not aware of what an NVDIMM is, it's basically a DRAM with NAND on that same unit, with a controller, special controller that senses when the power has gone down, and it will flush or get all that data saved to the NAND. Well, it needs power for that, right? You need to have power to come from somewhere, so it has a battery pack that is associated with that. Now, that's the traditional DDR4 NVDIMM, for example. As we look forward, I think some of the, and there's a lot of complications with that. It's a very niche market in terms of the overall memory market, but it's sort of.
And why is that, Andy? Why is it niche?
Like Pecan said, earlier, he said checkpointing and stuff like that, it serves a specific purpose. I think the biggest competition for NVDIMM, quite frank, is a UPS and a server on a UPS, right?
Right.
Yeah, go ahead.
Yeah, go ahead.
You're involved in
I can answer one more advantage of NVDIMM-N is, so if you look at the architecture of NVDIMM-N, the DRAM is the place where the data resides, or the excesses hit the DRAM, and DRAM has infinite endurance. One thing we have missed in the whole, an attribute we have missed in persistent memory applications is the reliability for part of it, which is very critical for any memory module, because even a single bit flip can bring down your entire system or introduce a security hole. The NVDIMM-N has the highest reliability because your data resides in the DRAM, which has high endurance, and only gets backed up into the NAND when there is a power loss, maybe a couple of 100 times in whole lifetime. Compare it to something else where, like a NVDIMM-P or NVDIMM-F, that was a concept introduced long time back, where data hits the flash. So now you are seeing that the flash will get a lot of write amplifications. When you are hitting 64 bytes of data directly to the NAND flash, you will eat up its endurance, eat up its reliability very fast. So these are the two things.
Yeah, let's get and let's see if we can get back to Andy. And where does this go in the future? You know, how did, again, CXL attached persistent memory? What is SMART doing about this? Thinking about it?
Yeah, I mean, there's two questions there, right? Size and cost that came in. So back to the size question. So your size challenge because you're trying to integrate a lot of things into a tight, small space that was defined just for memory. Now you're putting NAND and other components in there. So capacity and size, unfortunately, is always going to be a little bit smaller. But I think one of the things we're trying to do there on the CXL front, CXL allows you to do something a little bit nicer with respect to memory. The first thing that most people probably may or may not appreciate about CXL is it's now the first time you got a plug and play environment for memory. You know, you can actually physically push in a module E3.S, for example, into the front of a server. You couldn't pull out a DIMM before, right? And just expect the system to keep running. So I think one of the benefits that is it's a FRU, it's a serviceable unit. Before you had to take the top off there, replace an NVDIMM, you know, with its battery back as two separate units. We have the opportunity, and what we're working on here at SMART is integrating those two. So you actually have both the battery pack and the ND, you know, and the RAM all in a single unit. That makes life a whole lot simpler for being able to remove and service, you know, the unit. So I think that's number one.
Is that going to be more cost effective than an NVDIMM?
I think it's going to be more serviceable. I think, you know, I think
still at high cost. You're still going to have NAND plus DRAM.
You've always got the added cost, yes, of course. I mean, you've got the added cost NAND and the battery pack. So that's number one. I think in terms of the cost element, I still think until we get something beyond, you know, the Optane was on a good path, but obviously, you know, we really would love to see something that doesn't involve an energy source. Clearly, I think would be the ideal solution for the industry. And I think that's a tougher one. There are other companies out there, you know, that are trying to address that problem. I think we're still.
So let's throw in a question here that came up, and just want to spend a little bit of time on it. Anyone working on a persistent memory that's dual ported? Current NVDIMM-N usage for my company requires to synchronize in software via PCIe and using the CPU and DMA resources. Any thoughts about doing a dual ported device there, Andy?
Absolutely, yeah. I think that's on the cards. If you look at any CXL roadmaps, the whole thing about CXL was the ability to pool memory and share memory amongst multiple CPUs. So
you just made that attendee very happy that there is a product coming from SMART. So attendee that asked that question, please get in touch with Andy at SMART and he'll solve all your problems. I want to go back to something that David talked about and really get into that a little bit more, because there's another question here that this will lead into. But now we're talking about this network. We have this huge network of nodes that's all connected. In terms of memory, it's cache coherent, connected all the way through. And, you know, Andy, you talked about having a device that you can plug in and plug out. What if that device is a bad actor? What if it's a malicious actor? You know, doesn't that bring down the whole network? I mean, it just doesn't bring down one server. I mean, it's great, the serviceability, you can plug and play memory, but this is bad. You know, this could bring down, does this bring down a whole rack, a whole data center? David, how do we deal with that kind of malicious or bad actor or even unintentionally bad actor?
Yeah, we're addressing that from a multi-layered, tightly coupled with our customer approach. So, if a bad actor has an insurgence at the drive level, maybe it's the memory-semantic SSD level, we want to quarantine and take that out of the equation, that device. At the same time, you don't want that insurgence to propagate through your overall system. And of course, today, OEMs and ISVs and system integrators have software-based detection mechanisms to minimize the risk of such threats. But what we're beginning to look at Samsung, at least beginning to look at, is how to detect at the drive level to complement and even improve the risk tolerance that systems and applications require. So
Any other comments? Gary, you have a lot of familiarity with storage and some of the things you have to do. How at Marvell are you applying this thinking to the controllers and products you're planning to develop for that CXL ecosystem to prevent this kind of issue? Make sure that there's high availability for the entire rack and data center.
Well, I mean, I think, David touched upon it whenever he was talking about it being done at the device level, then all the way up to the system level. But it also needs to include points in the infrastructure, just like you do with NVMe, is that you have ways to isolate the devices that go rogue. Those same approaches would have to be applied, of course, in a different way for CXL type devices to prevent, a whole rack. If the whole rack is attached to, say, a memory appliance, you do want to have mechanisms in place to protect it from rogue actors.
Yeah.
And,
Pecan, anything to add there?
Yes, I wanted to add, similar to what Andy said, we do have devices which have multi-ported CXL interface. So obviously, if to your previous question, I can be also a point of contact.
Okay, attendee, please contact Pecan at Intel for more information about dual-ported devices. Please go.
You can include me too.
Oh, and Marvell. Yeah, now you made that attendee very happy. There's multiple sources. Great. Keep going.
But to answer the question, for the high availability, when you take anything and distribute it over the fabric on a different nodes, it automatically adds resilience, because now you're not making anything centralized, which is prone to attacks or faults.
Interesting.
So we apply the same concept to CXL when or a pooled memory, which is disaggregated memory. When your memory goes out, it need not be on the same rack or in the same node. It can be distributed across nodes. Probably if the racks are very close, meets the distance, they can be across the racks as well. And that adds the resilience part of it. In addition to that, you can have multiple top of rack switches with redundancy network. So all that together will improve the resiliency of the overall memory system.
Got it. And any of the other panelists want to chime in on that?
Yeah,
system resiliency.
I agree. Actually, there was a great report put out by ATIC, I think, about the cost of downtime. Memory was a big component of that, along with many other things. But I think they actually put a number of something like $300,000 for single hour downtime. It's what it's costing companies now, when it goes down. And again, memory's not the sole reason, but it's one of the contributing factors. So we've been focused a lot on that over at SMART. So I think from that standpoint, memory, downtime has become a much bigger issue for people. And I think RAS features, from the server side have been a really important addition. I think you'll see the obvious trend is a lot of that as we go CXL gets pushed to the CXL controller level as well. So a lot of the SMART products and other panelist products here are going to have those RAS-like features where you can recover from dead spots. NVMe storage, we've known for a long time, we've been able to kind of, kind of just push aside those bad blocks, right? And make sure you're just using the good stuff and you reserve space for that. Well, you know, CXL and NVMe
yeah,
kind
let me ask you to build on something as well here that we talked about in our preparatory calls, Andy, is, you know, NVMe has developed a lot of capabilities. Do you see NVMe and some of those capabilities moving into the CXL space and even helping out CXL attached memory with some of these things like the undeterministic latency? You know, would zone namespaces move into
interesting. Yes.
memory?
Yeah, what's interesting is I think as storage guys who've been familiar with controllers, you know, for a long time, being in between you and the media, right? DRAM has been something where you go straight to the media a lot. I've been very familiar with that growing richness of features that you start to see in the controller layer. So absolutely, I think we're going to see a lot of those things borrowed, you know, in terms of things like firmware attestation models, you know, hardware root of trust is becoming important, for example, you know, so being able to have a intelligent controller that you can talk to verify that you're a bona fide, you're a validated component in that system. You can now do that, right, with things like memory-based, CXL-based memory solutions. So all those solutions have been there in NVMe. You see those kind of management level functions already starting to creep in. RAS is something unique, of course, to more of a memory architecture, but we've had bad block management in NVMe. There's a lot of parallels, absolutely a lot of parallels I'm seeing.
So Gary, what can we learn about SSDs and how they were adopted? And how can we apply some of those lessons learned to CXL attached or persistent memory in general getting adopted? What do you see there as being good learning that informs us?
Well, you know, whenever we, you know, first introduced NVMe to the industry, it took about 8 years before it hit that hockey stick of adoption, and it was, you know, widely used. Now, one of the things you can compare itself to is saying that, well, there was fast and SATA SSDs already in existence, and so you had these incumbents, and so customers were fairly happy with SAS SSDs, and so there was not a big reason to move to NVMe until they got to the speed it became more cost effective. Now, when we look at CXL, there are some differences in that with CXL, there is nothing comparable to it, at least nothing that's been standardized. And so we're not able to add memory, as Andy was saying, is that it's serviceable. But even more important is that we have memory that can be shared across multiple nodes, which is a game changer. And I'm not talking about just being able to parse out different areas of memory. We're also able to access the same data between the same nodes once we get to CXL 3.0. And that's, I mean, while it's going to be a big lift, being able to manage these systems that are clustered together and accessing the same memory and the same data, but it's going to bring a lot of advantages to the overall infrastructure, to the overall solution. But to go back to your point about what can we learn from NVMe, I think the RAS is going to be the biggest part of it, especially when we get to persistence, and we have to maintain that data once power is either lost intermittently or if it's powered down and brought back again. And so some of those same capabilities around endurance, retention, and so forth that we're all very familiar with in the, you know, SSD world are going to be applicable whenever we go to using persistent memory in CXL.
Got it. Okay, we're down to our last 5 minutes, and so this will be the speed round. Each of you will get 30 seconds to talk about how we're redefining persistent memory. It seems like we're saying persistent memory is not dead, and we're seeing it longevity with a combination of NAND plus DRAM, although with or without an energy source, with what kind of interface. There's still a lot of Cambrian explosion of experiments going on right now. David, you get first in speed round. Redefining persistent memory, go.
Persistent memory is fully appreciating application requirements from a serviceability, performance, and continuity perspective. By engaging with the application developers and leading them through hand in hand on what our technologies can do from a memory and SSD standpoint, that's how persistence will get an attach to bigger markets and drive not only CXL, but new applications and opportunities.
As a good marketing guy, you exceeded 30 seconds. Thank you, sir. Andy, your 30 seconds. Go.
I think we're going to see a lot of innovation over the next year or two in this area. I think there's a lot of stuff that needs to be done. People want big memory, big capacity memory at memory speeds. There's no question. And I think CXL goes a long way to solving that. From a persistent standpoint, the same thing applies. They want bigger than what we can provide today in NVDIMM. So I think you're going to see a lot of innovation around getting more capacity and getting, .mem SSDs. I think Samsung's been great in leading that kind of charge there. I think has a lot of potential to meet some of that challenge as well. And I think, again, next 1 or 2 years, now CXL systems are out there. I think we'll see a lot of innovation as people start to attach more creative devices to that bus.
Thank you, Andy. Never short of words. Speak on.
I think the end user or the users of persistent memory now should focus on the applications part of it and leave the rest to the implementers like Intel and others here. For example, with FPGAs, you can take the memory or get the data from CXL interface and shove it back to the NVMe SSD behind the scenes, or take it over the fabric over Ethernet, or shove it within the system or on the card using an NVDIMM. All those implementations or nuances are left to the hardware folks. The actual user should just focus on the latency, reliability, and the cost aspect. Once you solve these three, the rest to the hardware folks, they will figure out the right implementation for you.
Makes a lot of sense. Gary, take us home here. Final word, persistent memory, and how should we define it?
Okay, well, I mean, I think it just kind of goes back to what I was saying, that there are technologies that are before their time. I think persistent memory, where it does have a lot of value. Right now, whenever you bring CXL into the industry, CXL has taken up all the oxygen in the industry. And so right now, CXL is using DRAM for memory type applications as a pipe cleaner. So once we get CXL implemented and we have all this plumbing in place, and then we get to that, past 2 NUMA node latency solutions, then we're going to start to see that persistent memory is going to have a place. And then once we get that, persistent memory adding value at the lower cost and the higher density, then we'll look at the value of persistence. And I think CXL also adds, as Andy was saying, is that it gives us serviceability that we never had before when it was implemented as a DIMM. We now have it in a drive type form factor.
Thank you very much. I'm going to give all you guys a round of applause, because if we were in person, great job. Appreciated having you. Let me wrap up with a few slides. Remember, none of this has been advice, and you use at your own discretion and risk. What was that comment? I can't quite remember. But as an attendee, you have action items. Please rate this webcast and provide us with feedback. Of course, we always want 5 stars for doing a great job. We definitely thank our panelists for giving us that knowledge. There's a Q&A from this webcast, which gets posted to this blog. And we'll try and answer some of the questions that we didn't get to in time here. There's some really exciting events coming up where you can learn more about memory usage. There's one called MemCon, which is coming up here at the end of March. SNIA related, we're having the Compute, Memory, and Storage Summit, which will be held over 2 days. This is a free summit. It's going to be fully online. You can find more information at SNIA.org and the CMS Summit. And then finally, this webcast, SNIA is also an educational organization. And this webcast and many other videos, presentations are available there at the Educational Library. Please join SNIA if your company's not already a member. And please look at joining the Persistent Memory SIG, which is also a place where we talk about these issues. So again, once again, thank you very much to our panelists from Marvell, Intel, SMART Modular, and Samsung. Thank you for joining.
Thank you.
Thanks, everyone.